Welcome to Quick MCAT Lessons, where I try to explain MCAT topics in 10 minutes or less. Today we're going to talk about the quantum numbers. So far we've talked about Bohr's model, where electrons orbit the nucleus in fixed energy levels, labeled by the principal quantum number n. That model was a major leap forward, but it turned out to be too simple. It only really works for hydrogen and doesn't fully explain more complex atoms. As scientists dug deeper, they realized that electrons don't move in neat circular orbits. Instead, the positions are better described by probability clouds or orbitals, where we can talk about where an electron is likely to be. We don't know where an electron will be with certainty, and this is explained by Heisenberg's uncertainty principle, which says it's impossible to simultaneously determine with perfect accuracy the momentum and position of an electron. If we want to assess the position, it has to stop moving, thereby removing its momentum, and if we want to assess momentum, it has to be moving, thereby changing its position. To describe these orbitals and the behavior of electrons in atoms more accurately, we need a more detailed system, and this is where the 4 quantum numbers come in. So what are quantum numbers? Quantum numbers don't specifically tell us where the electron is, but they tell us the region where it's most likely to be found. They tell us what energy level it's in, what type of orbital it's in, how that orbital is shaped and oriented, and even which direction the electron is spinning. Now, each electron in an atom is described by a unique set of 4 quantum numbers. Together, they define the electron's probable location and its properties. Also, no 2 electrons can have the same 4 quantum numbers. This is said by the Pauli exclusion principle. Now let's get started with the first quantum number, or the principal quantum number, n. This is the one that Bohr originally introduced. It tells us the main energy level, or the shell the electron's in. It's a positive integer, so 1, 2, 3, so on. And as n increases, the electron is further from the nucleus and has more energy. Now I think of this as floor numbers in a building. So you know how whenever people work, they're like, oh, I work on the 63rd floor, I work on the 50th floor. The higher up you go, usually the more powerful you are, and you could say the more energy you have. And the more energy you have, you'll have more space, you'll have your own office. But if you're like down at the bottom floors, you have like these little cubicles. Obviously that's not true for every building, but that's just what I like to think of. And so from there we can talk about the quantum number 2, or azimuthal quantum number, which is also called the angular momentum quantum number, and it's denoted as L. This number defines the subshell or shape of the orbital within a given energy level. So for any value of n, L can be any integer from 0 up to n minus 1. Each value of L corresponds to a type of orbital. So if L is 0, then you're in s orbital, which is spherical. If L is 1, then you're in p orbital, which is like a dumbbell shape. If L is 2, you're in the d orbital, which is like a clover shape. And if L is 3, then you're in the f orbital, which has complex shapes. So if n is equal to 3, then L can be 0, 1, or 2, meaning the third shell has S, P, and D subshells. And if n is only 1, then L can only be S. And so L can be up to n minus 1, or it can be anything lower from 0 up. And so the third quantum number is called the magnetic quantum number, and it's denoted as M and with a subscript of L. This number tells us the orientation of the orbital in 3D space, like whether the orbital is pointing along the x, y, or z axis. So for each value of L, ML ranges from negative L to positive L, including 0. So if L is 1, then ML can be negative 1, 0, or positive 1. This tells us how many orbitals exist in a subshell. So if L is 0, then there's 1 orbital, because you just have L, right? If L is 1, then you have 3 orbitals, because you have negative 1, 0, or plus 1. If L is 2, then you have 5 orbitals, because you have negative 2, negative 1, 0, plus 1, plus 2. Same thing for if L is 3, then you have 7 orbitals. And so each orbital can hold 2 electrons. And so S subshell can hold 2 electrons, P subshell can hold 6 electrons, the D subshell can hold 10 electrons, and the F subshell can hold 14 electrons. And finally, the last quantum number 4, is called the spin quantum number, and it's denoted the same way as the third one, but the subscript is S instead of L, so it's MS. Now, this can describe the direction an electron is spinning within an orbital. It can either be plus a half or minus a half. Electrons in the same orbital must have opposite spins. This is also part of the Pauli exclusion principle, which says no two electrons in an atom can have the same set of all four quantum numbers. So for example, one electron in an orbital might spin up, which is positive 1/2, and the other spins down, which is negative 1/2. Two electrons in the same orbital with opposite spins like this are said to be paired. Electrons in different orbitals with the same spin quantum number values are said to have parallel spins. If you want to determine how many electrons can be within a shell, you can use 2n squared. This tells us the maximum number of electrons within a shell. If you want to know the max number of electrons within a subshell, use 4l plus 2. These formulas tell us how, with increasing shells and subshells, allows more electrons to be in there. Electron configuration is basically a map of where electrons are in an atom. It tells us what shells, subshells, and orbitals they occupy, and they don't fill randomly. They follow a specific set of rules. And these rules we will go over next time.